Hello, I'm Dr. Nicholas West, the spectroscopy specialist at Andor for Europe, Middle East, Africa, and India. And in today's video on iStar sCMOS cameras, I'm going to go through some demos and a bit of background information on standard external triggering practices and how to troubleshoot them as well. So I plan to approach this from being able to give very beginner introductory level information, but then in some instances I go on to very advanced content gradually. So I hope that both beginners and more advanced users will be able to take something out of this video. To begin this presentation, I want to go a little bit into the background of thinking about how do instruments synchronize with each other. When I think about using the nanosecond timescale and/or iStar cameras, there are a few more considerations that you might have to take into account as compared to when using a millisecond camera. So, for example, if you have a shift in when that pulse arrives at the camera of 100 nanoseconds, that may not matter for a camera that is operating on the millisecond timescale, but it can be the difference between making a good acquisition and not acquiring any good data at all with an iStar nanosecond resolution camera. So to start thinking about maybe a relatively simple way of synchronizing two instruments with each other with electrical pulses, I want to consider the example where you may have instrument 1 in green on the left and instrument 2 in orange on the right. And you want to ask the question, how can instrument number 1 tell instrument number 2 to start? So this can be accomplished by first sending a coaxial cable from instrument 1 to instrument 2, and then sending electrical pulses along this coaxial cable. So to give a quick description of how a coaxial cable works and how it's made, you can see that in the middle of the cable there is a copper wire to allow the electrical pulse to travel along the wire. There's insulation to make sure that it doesn't make electrical connections with other things in the room. There's then often a mesh of some sort surrounding the cable to try to reduce the influence of electromagnetic radiation in the room affecting the signals you're trying to send along this cable, as well as an outside insulation layer. You may be familiar with coaxial cables from cable television plugs, but the plugs in the lab have often somewhat similar yet slightly different connector types. So the two that we'll be discussing today that you may see most often in the lab are called SMA and BNC connectors. So the SMA connector is here. It's a screw-on type connector that is usually used when the connectors do not need to be moved from one instrument to another to change the experimental configuration quite as often. However, for the BNC or bayonet type, there's a little bit of a bump on one of the sides of the connectors that fits into a groove on the second connector that when you turn it around maybe a quarter to a half turn or so, it locks into place, but it can be much more quickly detached and moved from one instrument to another. And so here you can see what's called the male side because it has a pin coming out of the middle of the cable, and this side is most commonly on the actual cable side, whereas the female connector is most commonly on the instruments themselves. So now that we have a coaxial cable going from instrument 1 to instrument 2, instrument 1 can think, let's start. I will send a TTL pulse. So you may ask, what is a TTL pulse? So it is a transistor-transistor logic pulse that's in the shape of a brief rectangular shaped sharp jump in voltage. And so what that looks like is the signal normally is at 0 volts, and then it rises up to anywhere from around 3 to 5 volts or so, and then falls back down again. And so you can see that this pulse travels along the cable from instrument 1 to instrument 2, and it has a finite speed of travel of somewhere around 30 centimeters per nanosecond, depending on things like what type of material the cable is made out of. And so if you have a, say, relatively shorter 10-meter cable, this pulse will require somewhere around 67 nanoseconds to travel the length of that cable. Whereas if you have a relatively longer 50-meter cable, it can take up to, say, around 334 nanoseconds for that pulse to travel from instrument 1 to instrument 2. So once that pulse arrives at instrument 2 needs a way to detect that pulse. So what it's waiting for is it sets a threshold of voltage level that will let it know that a pulse has arrived, so that when that voltage goes from 0 volts and crosses that threshold, then it knows to start doing its job. So once a pulse arrives to instrument 2 and it's been detected, instrument 2 will say it needs time to think about starting its job. So because there are electrical circuits within instrument 2 that tell it what it needs to do, that those pulses need to travel within the instrument 2 itself as well. So this can typically take anywhere from about 10 nanoseconds to 1 microsecond for instruments to think about starting doing what it's been told to do. And so in total, if you add together the delay in the instrument starting its job as well as the delay of the pulse traveling along the cable, this can be anywhere from typically about 10 nanoseconds to microseconds of time between when instrument 1 wanted to tell instrument 2 to start a job and when instrument 2 actually is able to start a job. Now that we have discussed the basics of how multiple instruments can communicate with each other, I want to discuss a few of the different types of instruments you might see that scientists often use to communicate with each other in the lab. So the first example is a digital delay generator that usually have sub-nanosecond timing resolutions, sometimes abbreviated as DDG. So these generate TTL pulses to send out to other instruments. So you can see that they often have multiple B and C connections. So here's a variety of photos from different ones that I've used in different laboratory settings. And they often have controls to determine the sequence of the timing of sending out the pulses to, say, orchestrate a variety of instruments at the same time in the lab. The second type of instrument that I would like to discuss is called an oscilloscope. These are used to visualize the electrical signals or pulses that are sent between different instruments in order to do troubleshooting of the synchronization. So quite often they will have a screen where you can see different types of electrical signals and when they arrive to the oscilloscope in time, as well as, so here's another one with a screen, some B and C plugs on each of those. In this example one, they may not always have a screen. In this particular type of oscilloscope, there's a USB connection to the computer where then on the computer screen you have a window that shows the sequence of timing. And here's one other one that I've seen previously in the lab. And finally, I want to discuss a small variety of other types of instruments that you might see in the lab as well. These include lasers and detectors and other pieces. Pictured here are a small sample of some of them that I've used previously in the lab, but there are far too many different kinds for me to show in any one slide. But to give you a brief example of how some of these instruments are used that often accept or sometimes pass on TTL pulses to other instruments to synchronize the entire experiment. The first is pulsed lasers, and these are commonly used for sample excitation. So in this photograph, you see an excimer laser with the side panel off. Right next to it here is a YAG laser, and the next type of instrument that I want to show you is a 1D light detection instrument. So these include photodiodes, PMTs, CPMs, power meters, and so You can see here's a CPM with some of its electrical connectors, as well as a power meter that I opened up one day when I was doing some troubleshooting in the lab. And lastly, there are 2D detectors, so cameras in this case. I have pictured here is the iStar sCMOS. And so one thing that I want to point out is that a fair amount of these instruments in the lab have high voltage pulses in them that can be picked up on the signal when you're sending pulses from other instruments to each other. So I'll show you an example of that in a moment, but here in the case of an excimer laser, it uses kilovolt pulses across gas to create the lasing. There's high voltage pulses inside lasers. Sometimes you have gated CPMs and PMTs, so we can get onto that in a moment. So one of the difficulties with working on these highly advanced instruments that can create high voltage pulses is that all of these instruments can be working properly as they're intended to be used, but they can interfere with each other if you, say, get them too close to each other. So in this example, I want to show what happens when you have two instruments, A and B, that a high voltage pulse is sent from A to B. But in this case, the researcher may have accidentally got the two cables too close to each other for also the control of instrument 1 and instrument 2. So in this case, you can see a very high voltage pulse traveling down that line. And in a case like this, there are electromagnetic fields that are generated around cables, and they're much larger when you have a high voltage pulse traveling through the cable. And so that can induce an electrical signal in the other cable when it's right next to it. And you can see that it generates a secondary pulse traveling towards instrument 2. So this creates a difficult situation where you didn't intend a pulse to be sent to instrument 2, but you have that crosstalk between the two cables. And so this problem is worse with larger voltages, or the proximity of the two cables to each other, or poor shielding. So usually more expensive, better shielded cables will be less susceptible to these effects. And so in this example, instrument number 2 was tricked by instrument A into thinking that instrument number 1 sent a pulse. And so this is a situation you want to try to avoid. And here, just to give you another bit of background, when working with higher voltage pulses, you may see some of these specialized cabling going from types of instruments like A and B that are made for different voltage ranges and different experimental conditions. You have either MHV or SHV, and both of these have extra insulation and slightly modified connector types so that you can't accidentally plug them into the wrong type of instrument. And you wouldn't want to send a high voltage pulse into an instrument that is not capable of accepting high voltages. So just a few examples of high voltage or current pulsing instruments that I've seen in the lab are like gated CPMs or PMTs, excimer lasers, maybe even vacuum pumps when you start them in the beginning of the day. These things can interfere with each other. So now I want to think a little bit more about how Andor can help the customers working with large ecosystems of the types of instruments that I've just been discussing with you. So one thing to note is there are too many third-party instruments for any one person at Andor to know or to have ever used. So quite often there are third-party instruments that researchers will have that maybe, like in my case, I've used digital delay generators and oscilloscopes, but I may not know the exact model that the researcher uses. So in this case, really, it's the researcher's responsibility to know how to change the settings on their own third-party equipment. But we do want to try to help the researchers to solve their experimental problems. So Andor's responsibility is to give support to explain how the iStar or other cameras work. And so in order to troubleshoot things or to help explain how to use the equipment to achieve a specific goal, we have to use timing diagrams. So I'll show some more examples of this later, but this gives us a common language where we know what timing is required for the iStars, as well as the researchers will know how to configure their instruments through discussing through timing diagrams of when the sequence of events should happen. And so whenever we do have to troubleshoot how something is happening, we can have a theoretical idea of how the timing should behave, and then we can test our assumptions of the functionality of the instruments. And first of all, is what we wanted to happen in the timing diagram actually happening through looking at the oscilloscope, as well as we can double check that everything is functioning as it should in the camera when troubleshooting. So before I get into a few real-world examples of how the iStar sCMOS can be used with the different types of instruments that I've just been talking about, I want to do a brief background review of the internal components of the iStar sCMOS so that everyone remembers how this camera functions. So pictured here on the left, we have an Andor iStar sCMOS camera with a lens on the front of it. If you look in the front half of the iStar sCMOS is where the intensifier is in the camera. So here are the components that make up the intensifier as well as the sensor. So in the beginning, when light comes in to the intensifier, it comes in through the input window where there's a photocathode substrate. So that photocathode converts the photons into photoelectrons that travel to the microchannel plate. However, this photocathode is what has high voltage pulses that allow for the very quick nanosecond timescale shuttering of the iStar sCMOS camera. So once those photoelectrons come from the photocathode to the microchannel plate, there is an amplification of that signal because there's a voltage that's applied across the microchannel plate. So when the photoelectrons hit the walls in the channels of the microchannel plate, every time it hits a wall, it has the possibility to create more electrons that come off of the wall, and so there's an amplification of each electron collision on that wall through the channel as it's traveling through the microchannel plate. So after that, that cloud of electrons that's generated from each electron, each photoelectron that's come into the microchannel plate, that whole cloud travels to the phosphor screen where that signal is, these electrons, this cloud of electrons are converted into visible photons that are in the wavelength of the high quantum efficiency wavelength range of the sensor in the camera. So that light is then sent to the appropriate place on the sensor by sending it through a sensor to intensifier coupling. So usually this is either fiber optic bundle or lens coupling. And lastly, there's a 2D sensor, either a CCD or an sCMOS sensor. Most of the sensors we're focusing on today are for the sCMOS sensor. Okay, now that we've gone through all the background, we can start thinking about maybe one of the most simple types of acquisition, the single scan. So here I want to give a brief experimental setup showing how a single scan will work. So first of all, we have a digital delay generator that's connected to a YAG laser and an iStar sCMOS camera. So one point I wanted to make here is that you can see that this wire is shorter than this wire here. And so the reason I put this in is that quite often researchers will just have different types of cables available to them in the lab, and so maybe they'll just select whatever cable's most readily available to them. And so there's no real reason in this case that I would choose the shorter, longer cable, except that it's just what's available. So I wanted to show you what would happen if you do connect shorter and longer cables. So in this case, you can see the pulse is generated by the digital delay generator, and you can see it's taking a lot longer to travel from the long cable to the iStar than it did with the short cable. So now that those pulses have been sent, both of these instruments, the laser and the iStar, are preparing to do their jobs. And so you can see that the laser will fire at the sample, and it will create some laser scatter and some emission from the sample, and then subsequently this travels to the lens and the sensor and all the components of the iStar camera. The laser stops and the acquisition is finished. So let's think about the timing of what's actually been happening here. So in all of these plots, I'll show a couple of plots overlaid on top of each other, where if you go from left to right, you start from the beginning of time to later in the experiment. And so the event that we're actually looking at generated from the laser is happening on this line. And so you can see right here is showing when the laser hits the sample and it's creating some emission. And so this first peak in this case is actually laser scatter from the laser light bouncing off the sample. After that, some of the absorbed light from the laser gets re-emitted from the sample, and that's the actual signal that we want to acquire in this particular example. And so this is, from when seeing this signal, we can see why now we want very quick gated nanosecond timescale resolution, because there's this initial laser scatter that we do not want to measure. And so this is typically maybe picoseconds or 10 nanoseconds or whatever the time scale of this laser pulse is approximately what the width of that scatter light might be. And so we don't want that to reach the camera sensor, but we do want to open the gate to allow for this signal to reach the camera sensor. So what's also happening now is that this external trigger also goes to the camera, and after a little bit of time for the camera sensor to think and get ready for its acquisition, the sensor itself is allowing for the exposure to happen. So the exposure time is starting. However, no light is yet reaching that sensor because the intensifier gates and allows whether or not light is going to actually reach the sensor. So after a specified time delay that you can put into the software, the gate actually happens, and that is what controls which section of that signal you're acquiring. So overall, we want to make sure we're not acquiring excessive other signals that we don't want to be in the camera, as well as we want just long enough of exposures and gating to acquire the signal we're looking at to not create too much dark count during the acquisition. So now I want to show a slightly altered version of this if you want to examine what is actually happening in the camera when we're actually sending this signal to the camera. So instead of hooking up the laser, at this point I'm going to show you connecting everything from the camera and the delay generator into an oscilloscope to observe what the timing sequence is. So in this case, we put a BNC-T on the digital delay generator to split that external trigger between the iStar sCMOS external trigger plug and channel 1 on the oscilloscope. Quite often, I would plug in this channel to the oscilloscope first to double check that the pulse that I want to send is the right shape and width and everything that I desire before sending it to the iStar sCMOS. And so when you visualize that, you'll see a rectangular TTL pulse on the screen. The next thing I would do is I want to know when is my sensor exposing in the iStar sCMOS. So I would connect a cable from the SMA of the fire out, which gives you a pulse that shows when the sensor is exposing, into channel 2. And so then you can see this pulse that's arrived, and there's an exposure that happens after the trigger comes in. The next thing that I would want to monitor is I would want to know, when is the gate happening? And so in this case, we have a plug that you may have to pull off the rubber grommet in order to access this plug. But if you zoom in on that, there's right here this plug that you push in the special type of connector into that then gets connected to the gate monitor. And so in this case, the high voltages that are going to the photocathode are too high that we don't want to directly connect them into the oscilloscope because they could damage the oscilloscope. So the clever engineers at Andor wanted to use the concept that I was describing to you earlier about having a high voltage pulsing wire next to another wire to pick up the signal that gets sent to the oscilloscope. So that's what they did. They put a wire right next to the photocathode, and then that sends that signal in, and you can see that it's not a perfect TTL rectangular shape, but that's okay, because really we want to know when is the gate opening and when is it closing. And so what you end up seeing is this downward signal is happening when the gate is opening, and this upward signal is when it's closing. And you don't really care about the extra ringing that's happening afterwards, because all we really care about is when it's starting and stopping. So then we can zoom in on this, and once you zoom into a closer time scale, you can see a little bit more the noise that's in the background and the slight imperfections of the pulses that are generated. This is just very common in these instruments. And so you can see a sharp edge here. That's where you want to trigger off of. So you can see this little arrow is triggering off of right there, so you're not getting a less steep area to trigger off of. And so then you can see that after that trigger, the exposure happens after the sensor has a little bit of time to think and start its acquisition. And then the photocathode gate, this opening of the gate, this downward signal, happens with a bit of ringing. And so what we call this time before that gate opens, the insertion delay, that's deliberately put in to make sure that the gate opens once the exposure is ready to happen. As well as, again, there's a little bit of this AC ringing that we'll kind of think about a little bit more in detail about what ringing is in a later video. But just know that you don't have to care about this part at this time. All you really care about is this edge right here to let you know that's when the gate opens. Here's what that setup looks like in real life. So if I have this set up on a table, you can see that there's a digital delay generator here, the oscilloscope, and the iStar camera with some target that it's watching. And we have, in this case, all of the cables color-coded, because I find that sometimes with more complex experiments, you have a lot of different wires going around, and the way that I found to best organize it, in my opinion, is to color code with just a piece of tape each connection, so that I can know, okay, yellow on this side goes to yellow here, and so on. So now we've reached the first interactive demonstration. So you can follow along at home if you've got a digital delay generator, the iStar sCMOS, and an oscilloscope. And so I've put some of the most important settings that you may want to dial into these various instruments of your own. So here I have that the delay generator is set to 5 Hertz. I've added some delays. In this particular delay generator that I'm showing photographs of, I have to set channel A and B so that I can use channel AB with a little hat there. Setting A and B sets the width of that pulse. The other delay generators may vary, so you may have to make some of your own adjustments. And in this case, it needed a 50 ohm terminator on the opposite upside down hat. And I set that to a 50 ohm impedance pulse. So I did the same with the iStar. It is set to 50 ohms, as well as the oscilloscope is set to 50 ohms. And you need to add a small delay of the gate to make sure that the gate is happening after the exposure is happening. So we'll show you that in a little bit later. And then in order to get the right time resolution for the traces on the oscilloscope, you want to zoom in to about 2 milliseconds per division. So I will show this type of slide before each one of our demonstrations, so you may want to pause on this slide and configure your setup to look approximately like this. And then you can follow along and make adjustments to settings as I indicate them in future slides. And so the future slides, most of the setups will be quite similar to what I've shown here, but I will indicate in bold red the various settings that are changed from one experiment to another. So now, once you're ready to do the single scan externally triggered acquisition, what I'm showing here on the left are two screenshots of the same window with different tabs highlighted in the settings inside Solace that you can set up some settings, as well as the screenshot of the oscilloscope trace that you can expect to see when you put in these particular settings. So stepping through them one at a time, you can see that the acquisition mode is set to single scan. We put in a fairly low exposure time. We set the dynamic range, the sensitivity to 16-bit mode. We always start with the MCP gain down all the way to 0 because you want to avoid any possibility of damaging the intensifier unit. So whenever you're putting in new settings into the camera, I would always recommend putting it all the way to 0. And then after you start the acquisition, if there's any small pieces of the image that you cannot see above the noise floor, only then would I increase the gain just slightly, but always try to use the minimal amount of gain that is needed to see the signal so that you can still maintain your dynamic range. And so then the other settings I would set up is the width of the gate pulse here. You can also play with the delay of the gate pulse there. And so if you play with these settings here, as well as the exposure time, you should see that first of all, the exposure width of this pulse should be changed. The external trigger will be dictated by your delay generator, and your photocathode gate width and the delay from the trigger will be affected by these settings that you change. These other settings, the gain and the sensitivity, are more of settings that you'll see in Solace when you're looking at the image that the camera acquires. You'll see changes happen to those there. The next mode of operation to try in another demo is accumulate acquisition mode. So this is used when you want to take multiple acquisitions of a repeating phenomenon so that these images from those multiple acquisitions will be averaged together in post-processing. So this is after the signal's been digitized. It's primarily a post-processing way to take averaged images. So to set up this acquisition, you will change the acquisition mode to accumulate. You can adjust the exposure if you want, and you will want to change the number of accumulations from 1 to as many different images that you want to be averaged together. So again, I put a note here. This averages the images together after the sensor readout, so it's a post-processing effect. And especially anytime you make other changes to the exposure and anytime you start a new acquisition, again, start the gain down at 0 again and only increase it once you've determined that the signal is not too high and will not damage the intensifier. And then, as with last time, you can play with the delay and the width of the gate pulse and see that on the oscilloscope screen as well. So again, I would always test out with a low exposure or gate width and a high number of accumulations because this is a way to get better signal to noise. So often you're going to use this when you don't quite have as much signal as you would like in a single shot. And so there'll be more on this later because I will need to have a slide later to compare and contrast integrate on chip with accumulate mode. Both of them are ways to average signal together, but they're used at different times for different types of acquisitions. The next mode of operation is called kinetic series acquisition. This mode effectively repeats the single scan many times, but leaves you with an image for each one of those, as opposed to the previous accumulate mode averages them together. So here's for a timing diagram of the kinetic series mode. So again, it is everything right here was shown a few slides ago for the single scan mode. And so the only thing different is that this is repeated as many times as you tell the Solus program to repeat this kinetic series mode acquisition. So the biggest change from the previous slide in the settings to the equipment for this demo is that I would zoom out on the time scale or change to a higher repetition rate of the digital delay generator just so that you can see this process actually repeating multiple times on one oscilloscope screen. And so in order to do that, we have the same settings window in Solus you saw before, only we've changed the acquisition mode to kinetic series mode. And in this particular case, you can change the kinetic series length. That will determine how many single scans it takes to combine together into the kinetic series. And then you can play with the same settings as before, so always keep the gain down. You could play with the width and the delay of the gate. That should be the same for each one of those components of the kinetic series. So here I wanted to show you what would happen if you play around with some of those parameters. So this is essentially what you should see if you play with them at home. So first, I think I have the settings that I've been showing previously for a kinetic series with the images from the oscilloscope. And now in this other set over here, if you adjust the parameters like these to add more delay, more width to the gate, a longer kinetic series, change the exposure time, you can see all of that more or less happening on the oscilloscope screen. So you can see that the exposure time is longer as it's been changed. The gate width is wider in the one below, as well as there's a little bit more of a delay from the gate beginning to the external trigger than above. The next mode of operation is called gate step acquisition. So this is the same as the kinetic series, only the gate is the delay of the gate, or you can also change the width, is moved in each sequential scan of the kinetic series. So first, there's a quick example of what kind of things that you can do with gate step mode. So in this case, if you have some time resolved steps of a recurring phenomenon, so if you repeat this phenomenon happening multiple times and you want to watch it at subsequent time delays after the start of each reoccurrence, in this case, the researchers made a kinetic series video of laser-generated plasma bullets acquired from multiple time-stepped gated scans. And so what you should see is somewhere off to the right, I'm not sure the exact location, there's a cathode, and somewhere up to the left, I'm not sure the exact location over there as well, there's an anode, and the plasma bullet travels from right to left. And so now you can see that sequence repeating, and so each one of the images in this video series is from a repeating phenomenon that were then put back together to form a video of that process. So what does the timing diagram look like for this? So first of all, you have your events happening, that you have a repeating phenomenon that is the same each time. You then have your external triggers triggering both that phenomenon and the camera with some insertion delay. The sensor is then activated through the fired channel. You can see when the sensor is activated it has to be activated for the entire duration of the phenomenon that you're trying to measure, because all of these instructions are sent to the camera before the gate step mode is ran. And then to get your subsequent steps along your gate delay, you can see the photocathode gate, there's more and more of a delay for each iteration of each scan in this gate step mode. And so then you can see what happens when you move that gate to later and later delays with each shot is that you're actually sampling a later time in the phenomenon each time it recurs. So in order to test this out on your own equipment, again, always turn down the iStar gain whenever you're doing anything, but particularly when you're increasing the exposure and the gate delays. And on the oscilloscope, again, you want to be zoomed out a bit to make sure you capture multiple of these traces on the scope. And in this case, because we want to visualize a few of these in a row and troubleshoot what's happening, I found that I needed to push stop on my oscilloscope so that it's only ready to take one acquisition at a time. So I would then push the single trace button on my particular oscilloscope that I was using, and then I would push both the single trace and the take single acquisition in Solace at the exact same time to make sure they both started at the same time. So then once you actually have that in Solace and you're setting up your parameters and you're looking at what you get on the oscilloscope screen, you keep kinetic series mode as the acquisition mode. You, in this case, increase exposure time to make sure that you can cover the entire phenomenon. In this case, we're just showing 3 because that's how many we wanted to fit on the oscilloscope screen so that we could still see quite well the timescales of the gates and everything else. Again, turn your gain all the way down and then bring it up as you need later. You start out with some finite width of your gate and a low amount of delay or 0 delay. And it's very important if you want to do gate step mode is you actually tick this step box. And then you will have these options below that you can step either the delay or the width of the gate. And so you have a couple of options there. You can either have a constant step, an exponential step, or a logarithmic step. In this case, we just put in constant, and we wanted it to have a constant step of 50 milliseconds for each scan in this gate step kinetic series. And so what you can see on the oscilloscope screen is you have the repetition of the external triggers, and for each one of those you have an exposure of the sensor, and for each one of those you have the gate opening and closing. This one happens very soon after the external trigger comes in. The second one happens after a 50 millisecond delay, and the third one happens after a 100 millisecond delay. The next mode of operation is called integrate on chip, or IOC acquisition. So in this case, I want to compare the integrate on chip to accumulate mode, because both of these modes of operation are averaging together multiple pulses of a light source or of your signal, but they're doing it in different ways. So what I wanted to say here is that IOC mode is a feature very specific to intensified cameras. This is a way of pulsing the intensifier unit multiple times while accumulating the final electrons in the wells of the CCD or sCMOS before reading out one image. So to compare and contrast these two, as I've just said, you're summing together electrons within the well of the sensor. Whereas for accumulate mode, you are summing together the digital pixels values, or averaging them together. So it's a digital post-processing of the data. So for integrate on chip, the readout noise is calculated as it is in the spec sheet, because you're reading out one time, whereas the readout noise for accumulate mode is dictated by the average of images, each with readout noise at the spec sheet value. So you're having the same RMS readout noise multiple times and averaging them together to achieve higher signal to noise. So In the very specific cases when you do want to use IOC is when your signal that you're acquiring is happening faster than the sensor can possibly read out that signal. So then this is because the photocathode can be pulsed more quickly than the sensors can read out. So quite often this means that this mode is used when you have a very high repetition rate, low level of signal that you can accumulate electrons together to take advantage of those very fast light sources. Whereas the accumulate mode is limited by the readout rate of the sensor. So this is a slower overall process, but in total, whenever you can get away with it, you do want to use accumulate mode, because in integrate on chip, your sensor exposure is left on for all of the time in between when the gate is pulsing, and so it's accumulating dark noise. So you don't want to have an integrate on chip that happens for such a long period of time in between these shots that the dark noise becomes the important source of noise. So in the case of very far separated in time shots, you would always choose accumulate mode. So here's a timing diagram of this process. So again, you have your external triggers coming in, and then from the very first external trigger, this starts the sensor exposure, and the subsequent triggers do not affect the exposure until the predefined exposure time is done. So the only time that the next trigger will actually affect the exposure is after this exposure is done. If there's another trigger, it'll start a new exposure. Otherwise, this trigger is used for the photocathode. And so after each one of these other triggers coming in, you can see that there's the same insertion delay each time. And you're trying to take data at the same time delay at each time that repeated phenomenon happens to average together the signal. And so yeah, again, I'm just repeating here, it's useful when multiple low power laser shots are faster than the full frame readout speed. So if you want to test this on your own setup in a way that you can visualize on your oscilloscope, is in this case, I increased the repetition rate of the digital delay generator to 10 Hertz. Every time, turn down your gain, and then check the signal, and only then increase your gain. And the other thing that's changed is that in this case, I found it easier to trigger off of the fire signal, so that stays in the same position every time the oscilloscope is repeating acquisitions. So again, we're now looking at 10 Hertz. In this case, we increased the exposure, so and are taking multiple gates. So again, it's very important to turn down the MCP gain when starting this acquisition. We then have the width and these other settings you can play with, and then in this case you need to tick this integrate on chip box, and so you can see that in this case we're triggering off of the fire pulse here, and the first trigger creates an exposure as well as photocathode gating, and then the subsequent ones only have photocathode gates that happen, these ones, within that same exposure. So here's an example of a customer call that we were troubleshooting what was going on. That was someone trying to use the integrate on chip mode in order to do a LIBS experiment where they had a laser firing at 6 kilohertz, and they're trying to synchronize 6 kilohertz of the repetition rate of the photocathode with their laser pulses. So initially we would have a solace trigger, and we could also visualize on the oscilloscope screen when the laser was actually firing with a photodiode. So we could take a bit of scattered light from the laser and send it into the photodiode. And then in this case, when we looked at this on the oscilloscope screen, there was a difference in the triggers that were happening in solace and when the laser fired. It was maybe either a bit of jittering or stepping between these two. There was a little bit of a mismatch between the internal clocks of solace and the triggers. And so in this particular case, the user had gone into an advanced mode and had defined their own pulsing sequence. So they wanted 3,000 laser pulses per every exposure of the sensor and put it on 6 kilohertz. And so what this did is it made the camera do its triggers at its own internally specified rate that could be different or had different jitter and other properties than when the laser itself was firing. So what ended up happening is if you had the sensor that was coming in from the first solace trigger, and you can see that every time this phenomenon repeated, there was maybe a slightly different spacing between them with maybe a bit of jitter or so. And this is happening with respect to the laser from this external trigger, not the solace trigger. And so when there was an insertion delay from the solace triggers that were triggering the gating, you can see that this is not at all what we wanted, because the gating was happening at different times. This one completely missed the phenomenon. This one came a little bit early and got the beginning of it. And so when this customer wanted to look at different time delays individually, one acquisition at a time, what they were seeing was kind of a blurred average of this signal. And so they weren't really seeing this time dependence of their phenomenon. So we did some troubleshooting, went back to basic modes, proved that everything was working on the camera, and figured out, okay, what was really going on that was the difficulty with this current experiment was we did not want to use this advanced mode. Instead, we want to leave this, don't click on this advanced button, leave it on the default, and ultimately what that would do is it would mean that the integrate on chip would fire off of some external trigger source that could be more precisely synchronized with the 6 kilohertz laser. So in that case, then you can see that it's taking an average of multiple different photocathode gates that are happening at the same time window with respect to the time of the phenomenon. And so that concludes our first video. In a subsequent video, we'll be talking about how other combinations of these complex instruments together, even though each one of them can individually be working just fine, can complicate each other. So we're talking about effects of ringing and the electrical pulses, grounding, and jitter. Thank you very much for watching this video.